So in the video that I had you watch about polar molecules, the narrator went into some detail about the mathematics of it all and finding the differences in electronegativity, which is important and it's good background. But I understand from a couple of messages I've gotten that it might have been too much and it might have been confusing. So I want to bring it back as simple as I can, as simply as I can. Um, I had mentioned in class that the key was whether or not a molecule is symmetrical all the way around. But there's another way to explain it, which the two are just two different ways of saying the same thing, which I'll show you in a moment. But I wanted to walk through a couple of examples and show you the other method of determining whether a molecule is polar or not. So one is just look at the molecule overall and see if it's symmetrical. But there's another way to figure that out that might make more sense to you. So I wanted to show you that. So these are the types of molecular geometries that we're going to be working with. There are plenty of others, and in fact, in the simulation you did the other day, you went through a whole bunch that aren't on here, and I acknowledge that. But I want to focus in on these specific 6 geometries because these are the ones that we're going to spend the most time on. These are the ones that you'll be tested on. And given the method, the technique I'm going to show you for determining polarity, these are the ones that work perfectly using this technique. So the first thing you need to determine, you're going to draw your Lewis structure and then look at whether or not it has 2, 3, or 4 electron domains, right? So that means either bonds or lone pairs, keeping in mind that double or triple bonds only count as one domain. So the other way I always say to look at it is first count the number of atoms that are connected to the central atom. That determines the number of bond domains, and it doesn't matter if they're double or triple bonds. If there's an atom connected, that counts as one domain. 2, look for any lone pair electrons on the center atom only. Okay, so those are the 2 things you need to look for to determine the geometry. Those are also 2 of the things that you're going to look for to determine whether it's polar or not. All right, so there are 2 things that you need to look at in order to determine whether a molecule is polar or not. And this is separate from, but related to figuring out if it's symmetrical. So you can look at it, see if it's symmetrical. That is one way of determining it. Or you can do what I'm about to show you, which is another way of looking at the same thing. And I'll explain that in a minute. So the first thing you want to look at, once you've drawn your Lewis structure, are all the terminal atoms the same? So are all the atoms that are connected to the center the same element? So are they all fluorines? Are they all chlorines? Are they all hydrogens? If they're not the same, then you can kind of stop right there. The molecule is going to be polar for our purposes. If they are the same, you have a little more work to do. It might still be polar, depending on what happens with the second thing I'm going to show you. But if they're not the same, if there are any terminal atoms that are different from the other terminal atoms, if one of these things does not belong, then you can stop and say it's polar. The second thing to look at is the center atom now. Does that center atom have any lone pair electrons around it? If it does, the molecule is polar, regardless of whether or not the terminal atoms are all the same. Okay, so there's 2 factors to look at. Are the terminal atoms the same? And does the central atom have any lone pairs? So let's take a look at what that means with a couple of examples of each geometry that we're going to look at. When you have a linear shape, and you have a linear shape when you have one central atom and 2 bonded pairs, no lone pairs. Let's look at an example of a linear molecule. Linear molecule has 2 bond domains or 2 electron domains around the center atom, both of which are bonded pairs or groups of bonded pairs. Or the other way of looking at it, which is the one I use, is ask the question, how many atoms are attached to the center atom? In this case, there are 2 oxygens bonded to the center atom. That's how we know we're going to be on this, this chart. There are no lone pairs, so there's only 2 domains, one on each side. No lone pairs, so the shape is called linear. It's 180 degrees. That's as far apart as those oxygens can get. 180 degrees opposite across the carbon. So then the question of polarity comes down to, first of all, look at the terminal atoms. In this case, there are two terminal atoms, both of which are oxygen. So we can't use that yet to determine if it's polar or not because they're the same atom, same element on both terminal atoms. The second question is, are there any lone pairs on the central atom? The answer here is no. So we have two terminal atoms that are the same. We have no lone pairs in the center. Therefore, this is non-polar. Okay, so if you answer yes to the first question and no to the second question, then it's non-polar. All the atoms, terminal atoms, are the same, and there are no lone pairs. That makes it non-polar. Let's look at another example. Okay, here's cyanide. One carbon bonded to a nitrogen and a hydrogen. So how many atoms are connected to the center atom? Two. Two electron domains. No lone pairs. The shape is linear, 180 degrees. So the first question, are the terminal atoms all the same? There are only two terminal atoms, and they are different. Therefore, if you can't answer yes to that first question, that all the atoms around the outside are the same, it's polar. So just to quickly kind of tie this back to the way I explained it originally, you can see hopefully that this molecule is completely symmetrical, whereas this one is not. Okay, so asking yourself the questions about the terminal atoms and the lone pairs on the center atom is, again, just another way of asking yourself, is this symmetrical? However it works for you is fine with me. Let's take a look at 3 bond domains. Okay, so here is a central atom that is connected to 3 other atoms. Therefore, we're in this 3-electron pair row of the diagram. So it's going to be one of these two shapes. And then to determine the actual shape, we would look at whether or not there's bonding and lone pairs or just bonding pairs. In this case, looking at the center atom, the only things around that center atom are bonds. So 3 bonding domains or bond pairs means it's called trigonal planar. Okay, so it's a flat triangle. That's the fancy way that says it. Question number 1, are all the terminal atoms the same? 3 terminal atoms here. 2 hydrogen and an oxygen. One of these things does not belong. Polar. Okay, you have 3 terminal atoms. One of them is different. It's a polar molecule. I'm going to go back because I do want to show you an example that's nonpolar. So this is technically, or not technically, this is an exception to the octet rule. I mentioned there are a couple of exceptions. Boron is an element that only really needs 6 or can get away with only having 6 valence electrons. So this is a trigonal planar. There are 3 bond domains, right? 3 atoms connected to that central atom. No lone pairs. So it's again a trigonal planar shape. But this time we do have all the terminal atoms being fluorine. They're all the same. Okay, so we answered yes to that first question. They are all the same. Second question, are there any electron pairs around the center atom? The answer to that is no. There are not any lone pairs. So if you say yes to the first question and no to the second question, it's nonpolar. All the terminal atoms are the same, and there are no lone pairs on the center atom. It's nonpolar. I'll show you one more example. This is a bit of an odd one, but I wanted to show it because it is important. So here's a central atom, sulfur. It's connected to 2 other atoms, and it has a lone pair on top. So that's 3 electron pairs, the 2 bond regions, plus the lone pair, which gives us this shape, which is called bent. First question, are the terminal atoms all the same? Yes. Okay. Second question, are there any lone pair electrons around the center atom? Yes, there are. That sulfur has the lone pairs sitting on top. Yes, it's polar. Just to go back to my original point, this molecule is not symmetrical because the terminal atoms aren't the same. This atom, this molecule, is symmetrical because it's a triangle with the same thing in all three corners. This one is not symmetrical because it's got lone pair on top and then the two oxygen atoms on the bottom, so it's not symmetrical. Okay, so again, we're saying the same thing in a couple different ways here. Okay, now we're on to the 4-pair geometries. So the first one would be something like one I showed in class, right? CF4, and this has a central atom with 4 atoms connected to it. Okay, so 4 regions of electrons, 4 atoms connected to it, no lone pairs. So that's 4 bonds, no lone pairs. It's called a tetrahedron, okay, tetrahedral shape. Question number 1, are all the terminal atoms the same? Yes, they're all fluorine. Question number 2, are there any lone pairs around that center atom? No. If all the terminal atoms are the same and there are no lone pairs, it is not polar. Another example, CH3Cl. 4 atoms connected to the center atom. So we're in this row of the chart. All are bonded. So 4 bond pairs, no lone pairs. That's a tetrahedral shape. Question number 1, are all the terminal atoms the same? No. There's a chlorine mixed in with those 3 hydrogens. Polar. Okay, if you answer no to the first question, mark it polar. If you answer yes to the first question, but no to the second, but yes to the second question, mark it polar. If it's yes to the first and no to the second, it's not polar. So again, this is not symmetrical. It's got one terminal atom that's different from all the others. Makes it polar. Trigonal pyramidal shape. A nitrogen connected to 3 hydrogens. 3 atoms connected plus a lone pair on the center atom gives us this trigonal pyramidal shape. First question, are all the terminal atoms the same? Yes. Second question, are there lone pair electrons around the center atom? Yes. If you answer yes to that second question, polar. All right, last one. Bent shape. This is the one I showed in class. Water molecule. You have an oxygen connected to 2 hydrogens, so 2 atoms, 2 bond regions. Plus it has 2 pairs, so 4, 2 pairs of electrons. So 4 total regions of electron density, 2 of them are bonds, 2 of them are lone pairs. That is a bent shape. So first question, are the terminal atoms the same? Yes, they're both hydrogen. Move on to the second question. Are there lone pairs around the central atom? Yes. Polar. And again, just to make the point again, this is not symmetrical. It's not symmetrical because there are lone pairs on the central atom. Okay, and so again, different ways of looking at it. If this makes more sense, and then you don't have to think about even whether it's bent or not when you actually draw it. If you draw a molecule that has lone pairs around the central atom, mark it polar. Make sure that it needs those lone pairs, and you're not, because if your diagram is wrong, that's going to throw off your answer to these questions. But if you have a Lewis structure with lone pairs around the central atom, not these outside atoms, they're not responsible if they're all the same. If they all have lone pairs, that's fine. It's only the center atom where the lone pairs make a difference. So any lone pairs on the central atom, mark it polar. If there are terminal atoms that are not all the same, mark it polar. Otherwise, say nonpolar. All the terminal atoms are the same, no lone pairs on the central atom, nonpolar, end of story. Okay, so I hope that helps. And we'll go over some more of this in the next couple of days leading up to the test. All right, thank you.